Hey there, everyone. Thank you so much for joining us today. We are so excited to jump in today's physics webinar. While people are filtering in, I would love to kind of see people participating in the chat here. Um, All right, so go ahead and navigate to the chat box at the bottom of your Zoom window. It'll look like a little chat bubble. If you click that, you'll be able to type into the chat and make sure those settings are set to everyone. That makes sure that your comment is visible for everybody participating in the webinar. We will totally have time for questions and answers, and we want to make sure that we answer your question and that everyone knows what we're talking about. So if you're putting a question in the chat, make sure that's set to everyone. With all that being said, please let me know if you've joined us for a webinar before. I'd love to hear if this is your first time or if you are a Vernier webinar professional, you come to all of them, you know the names. All right, it looks like we have a few first timers. Perfect. And then some folks that have been here before. That's great. It's like a nice mix. Another first timer. Awesome. Perfect. And then some more folks that have been to a few. That is an awesome mix. All right, well, to make the most of our time today, let's go ahead to the next slide and I'll go over some housekeeping items and then we'll hop right into the good stuff. So just to cover a few ground items, you will receive a recording of today's webinar. It will be posted both on our website as well as on our YouTube channel in about 3 to 5 business days. That just gives us time to be editing that video, making sure that it is perfect. As soon as it's ready to go, we'll email it to you, so keep an eye on your inbox. And of course, it will be on our website and YouTube, as I stated before. You will also, in the email, be receiving additional resources as well as a certificate of attendance for today's webinar. I'm going to drop that in the chat as soon as I'm done talking, so you'll also have that right now. As I mentioned before, we'd love to answer your questions during today's session, so please use that chat box. Let us know if you have any questions, would like to see something. We're happy to get that going for you. If we happen to not get to your question, please reach out to us. We're available at physics@vernier.com. You can also give us a call or use the chat feature on our website to reach out to us. And with that, I'll pass it off to our fantastic presenters. Thank you again for joining us, y'all.
Thanks, Dylan. So today we're going to be talking about a lab from our Physics with Vernier book, Momentum, Energy, and Collisions. But before I jump into that, I'll just give a brief introduction. Tom Smith here. I've been with Vernier for about a little more than 9 years. Before that, I taught physics and engineering at a school here in the Portland metro area. With me today is Josh Entz. Josh, do you want to say hi?
Hello. Like Tom, I am a former physics teacher that now works at Vernier. I'll be monitoring the chat, so I will. I'll answer questions there, and important ones I'll probably interrupt Tom to so that he can answer those questions for everyone.
Very good. Thanks, Josh. So today I kind of have two goals with this webinar. One is just to give some details about the lab, talk a little bit about the different equipment that you can use to accomplish this lab in your classroom, and then the other goal for this is just to provide you with some tips for making this a smooth lab with just being able to let your students run with it, and a few tips that'll make it more accessible and meaningful for your students. The lab, today I'm going to be using graphical analysis software. You can certainly do this lab with Logger Pro and our wired sensors, but I wanted to be able to show you both our wired sensors and some of our wireless or Bluetooth Go Direct sensors as well. Let's see. From that, let me just talk a little bit about the lab. The nice thing about it is that it's pretty narrow in scope. It just deals with 3 types of collisions, a completely inelastic collision where two carts stick together, an inelastic collision where energy is not conserved, kinetic energy is not conserved, and then finally an elastic collision where energy and momentum are both conserved. To accomplish this, we're going to need to measure two things, mass and velocity. I'll show you in a second. I recommend a nice big electronic scale in your classroom so that you can get good measurements of the mass. It's not terribly critical because the carts are going to be the same mass or approximately the same mass, but you're going to get better results if you're able to mass your carts. And then velocity, that's kind of the meat of what we're going to be doing for data collection. And I'll show you a variety of different ways that we can collect velocity data. The other simplification of this lab is that it always starts with one cart stationary in the center of your track and the other cart having some initial velocity and colliding with the second cart. So that simplifies calculations and just allows students to really focus on what's going on with these three particular types of collisions. The equipment that we're going to be using, I'm going to go over this in some detail here shortly, but we're going to be using motion detectors and standard carts. Today, I'm going to be using the wired LabQuest motion detectors, but you can certainly use the Go Direct motion detectors as well. I'm also going to be showing you the Motion Encoder Carts, and then I'll wrap up with the Go Direct carts. So let me just dive into that. I'll minimize that for the time being. So you have here the scale that I pulled out of our physics lab. It's a nice 2 kilogram scale, so it's going to be hefty enough to be able to measure all of our carts. And I just brought this for show and tell, and I'm going to set it aside now and focus on the carts for the time being. The first cart we're going to deal with is just our basic cart from our dynamics cart and track system. It, 4 wheels and tabs on the end. Let me talk a little bit about the tabs on the end because we're going to use those in a variety of different ways today. What I have done, my personal preference, and that's all it is, my personal preference, is that I like to put the Velcro tabs on one end. So typically I would have the, I guess it's hook and pile. So this would be the pile side. And on the flip side, I would put the hook side. So I can still get those in there with that hook and pile on there. So that's what I would do with that end. And then with the other end, I put the magnet tabs. And again, making sure that all of my north-facing tabs have the same magnetic orientation. So this allows me to have a collision on one side that's perfectly elastic or close to it. And then on the other side, I can arrange for various types of inelastic collisions. Some teachers may prefer to do this differently, just the way I like to do it. I'm going to be using these with a motion detector, so I want to put my flag on this. This is the reflector, the motion detector reflector flag, I think is the official name. And I need the magnet tabs in place to hold it in place. And it just kind of flips into those spots there. So this is the first setup I'm going to use, but that's the cart right there. It occurs to me to mention right now that there are slots for different masses, but for this experiment, we're just leaving the mass of the cart as the only mass involved. There is an extension to this lab built into the end of the lab where students can investigate what happens for the different collisions with different masses. But for this one, it's primarily just the common the same mass. I'm going to set this aside, get that ready for our first experiment, and I'll bring out our motion encoder. So the motion encoder cart has this end on this side that has this motion encoder. It has basically an optical reader that when we look at the track, this is reading the bar stripe on the track. And from that, you get really good position data, and from that, velocity and acceleration. The trick for using this is to make sure that this line lines up with the line on the track, which lines up with the line on the, on the receiver. So this goes on the end of the track. The cart lines up with that. And there's a, let me turn that off. This is an infrared transmitter, and the receiver picks that up on the inside and communicates the position data to the software. I'll set those aside for a moment. We'll see those again. And then the last piece of equipment we're going to be working with is the Go Direct cart. And it's kind of nice because it has this encoder wheel on the bottom of it that gives us our position data. And it can work on track or off track. We're going to be using it on track for collisions. That makes a lot of sense just to keep things moving in the same direction. Has the same magnet tabs as the other carts as well. Okay, so we'll get more into the details of the carts as we get into the data collection. So at this point, I'm going to adjust my camera view a bit. There we go. Shrink that down, and I'm going to change camera views so I can actually see my cart and track system. So here I have set up a motion detector. This is, again, our wired motion detector. I am using LabQuest Mini for my interface for my wired sensors. It has digital ports and analog ports, and the digital ports are required for both the motion detector and the motion encoders. So that's the interface that I'm using. I'll just set that aside for now. And to get started with this lab, you would have already masked your carts and just recorded that information in your lab book, your lab manual, your handout. And you want to set this up so that the two carts are in the middle of the track. This is a 1.2 meter track, so I just put it at 60 centimeters where these two meet. They both have flags that face their respective motion detectors. There is a motion detector on the other end of this track. You just unfortunately can't fit it all into the view there. And so now what the software will have you do is, even though the motion detectors are going to detect, some distance to that flag, we're going to set a 0 point for this position. I have the two carts have opposite types of hook and pile on the ends, so they're going to stick together when they collide. And the other aspect of this is that you're going to want a common frame of reference. So we're going to call moving in this direction positive. So I'm going to change one of the motion detectors to reflect that change in direction. And we'll talk a little bit about that here momentarily. So let me go ahead and show the software here. I'm plugging my LabQuest Mini into my computer, and I have one motion detector connected right now, and it happens to be the one that you cannot see. So what I want to do at this point is recognize that this is the one I want to reverse direction. So I'll just do that right now. I'm also, I'm not sure that that's going to stay so let me just try this out. Actually, that motion detector, I'm glad I looked at that, is not the one that I want to reverse. So let me connect this other motion detector and we'll get it figured out here. So 2 motion detectors connected now. I'm gonna, to get started with, show you a nice tip about making this view a little bit more accessible for your students. So I clicked on the 3 dots up here, went to app preferences, and then I'm just increasing this scale factor. And what that does is increase the font so you can see a little bit better what's going on here. So in this case, I want to 0 both sensors. So let me do this. I'll just 0 this one. I'm going to not select reverse on this one. I'm going to 0 this sensor, and I will reverse the direction of this one. And just to make sure that I've done this correctly, I'm going to take the 2 carts and I'm going to move them, and they should have approximately the same value. So that's good. They're both moving in the same direction. They both have the same reference frame. The other thing I've done is I took a fair amount of time leveling the track. So I did that to minimize, these are low friction carts, but they're not 0 friction carts. So actually, you'll notice that, well, maybe you won't notice, but the end closest to the camera is slightly lower than the end up here, just enough to compensate for the friction involved with the 2 carts, so that we'll get more constant velocity as I give a cart a shove. Now, when I get ready to actually collect some data, I'm going to, again, set that at my 0 place, move this back here. We know that, let's get that set as close as I can to 0. So you'll see that this value is reflecting that negative position based on the new 0 baseline that I created. We only need velocity data, but I'm going to leave the position data up there just for a reference point. So let me go ahead and hit collect and give that a shove, and they collide. This again is a completely inelastic collision. We can hit the magnifying glass to see that collision. You can do the same here in the velocity. We have a little blip here with our motion detectors, which is not uncommon. If they, you can adjust the angle of the heads, for example, tilt them back ever so slightly so that they're not picking up anything from the track or anything like that. This motion detector signal is from our second motion detector, the one that you cannot see. So I just tilted the head back on that one as well. And the data that we want to pull off of this is really right in here, just the velocity right before the collision and the velocity right after the collision, excuse me. One of the, if you want to kind of toggle your velocity data, I'm just clicking in this timestamp right here and using the arrows on my keyboard, and I can toggle data point by data point. And so this looks like actually my first data point right before the collision, where my velocity for the first cart moving is about 4.3 meters per second. And then we come in here closer, and where they're together, I'd say that my final velocities are about 2.1 meters per second. And if I was, looking at my data table in the lab, we would have the masses of the carts, and then here we would put the velocities before and after for cart 1 and cart 1 and cart 2. So all the data tables are in the handout for the lab, which you'll have access to if you don't already. Students would then go through the process of calculating momentum and calculating kinetic energy for the carts and taking a look at whether those are conserved for this particular type of experiment. So let me minimize that. Okay, so that's collecting data with the motion detectors using the reflector cards there on the end of the carts. And I'm going to shift gears and bring the motion encoder just so you get a sense as to the difference in data collection there. So while I'm doing that, I'll just pull these off. And going to be taking both of the motion detectors off and unplugging them from my LabQuest Mini. Just to, for the sake of making sure the software knows what's connected, I'm going to discard that run, and it'll be looking for my next set of sensors that I'm going to connect here shortly.
Tom, one thing I'll mention while you're changing the experimental setup here is those motion detectors, those green motion detectors, just like the Go Direct ones, they have a dead zone, a zone where if you're too close to the motion detector, you won't get good data. And for the Go Direct version, and then also that green LabQuest motion detector 2, that dead zone is about 20 centimeters. So you don't want your carts to get closer than 20 centimeters to the motion detector. And the way that Tom attached those motion detectors to the track was using like a rod that kind of slides into the underside of the dynamics track. And that allows you to use the whole length of the track. Since they're mounted out there to about 20 centimeters away from the end of the track, you can really use the whole length of the track.
There's the rod that Josh is referring to now, and it just attaches with a thumb screw, and it slides into the bottom groove in our tracks.
Yeah, that mounting rod just comes with the cart and track system when you buy the bundle to the kit together. And if you don't have those, you can always just stack up some books, some textbooks or whatever on either end. But it's the kind of thing where if you put the motion detectors right on the track, which you could do, it just means that you have effectively a shorter track than the full length.
Thanks, Josh. What we're going to do with the motion encoders is the inelastic collision, but it's not, the carts aren't going to stick together. So the way I'm doing that is I'm just having the pile thumb tabs there on one side and just blank tabs on the other side. So when they run into each other, they're gonna, they're not going to stick together necessarily. Now the carts, you'll notice something unique about the track that I'm using. It has, typically you have a stripe, these striped tape down one side. I have applied another tape down the other side. These tapes are available for sale. I think they're like $15 or something like that. And so you can run 2 encoders on a single track. The carts have to be facing the opposite directions. You have to align this image of the stripes with the stripe on the track with the way that the receiver fits on the end of the track. It's just reversed over here. So we have stripe, 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 all in a line. It's important. Otherwise, there's nothing for the optical reader to see if it's on bare metal. Okay, So to get started, the carts require a couple of AAA batteries. Yeah, AAA batteries. And that's just to run the electronics in them. You turn it on by pressing the cart there, and you'll get a nice blue light shining there. That is not the infrared light. The infrared light comes out of this port here, which lines up with the striping again. So you want to make sure that when you line that up and you move the cart back and forth, that there's an LED on top of the receiver that also lights up. I don't think you can see it very well from this angle, but it's a good way to make sure that you're getting that communication going to the receiver and to your software. So once again, I'm going to put these two carts kind of in the center, make sure that both of the carts are turned on and the receivers are working. Like I may have overcompensated for friction a little bit with these, so I'm just going to raise up ever so slightly the track so that those will stay put. So there's the center. We're going to kind of do the same process here. I plugged the sensors into the LabQuest Mini, and I'll hit sensor data collection. And there we have our two positions identified. Typically, when you start the motion encoder, it's going to zero itself. I'm just going to hit 0 for that. And I'm also going to hit the reverse button because once again, I want a common frame of reference for both carts. Since we're looking for velocity, it's not terribly critical, but it does, it helps, I think, students kind of conceptually as well. So in this one, I'm just going to 0. And then we have our data collection set up here. I'm going to separate the two carts. Now with this, Josh was talking about the blinking of the motion detectors, the blinking area right in front of the motion detector. We can go all the way back to the receivers if we want to, as long as the cart is seeing the stripe on the track there. I'll go ahead and hit collect and give this a shove. And we see that they don't stick together, but we have, again, two, you can zoom in to look at that data. It's a pretty good looking picture there. And then over here on velocities, which is really what we're interested in, we're going to be picking off our initial velocity here again. And again, I'll just click in that time stamp and probably pull that data point off for my initial velocity for cart 1. And then once things settle out over here, probably there, just see how things are changing. So that's probably a good data point right there for my velocity for cart 2 of being 0.27 meters per second. And my cart 1 has a final velocity of 0.60. So again, students would be able to enter those velocities into the table and calculate momentum and calculate kinetic energy to see if either or both of those are conserved. Okay. So there's a couple of other ways we could go about looking at this. We could highlight a section of data and view statistics. This would allow us to get like the maximum value for our velocity before the collision. And for the blue, it would give us the maximum, well, let me go back, and the minimum velocity after the collision. So we could pull data off that way. We could then look down at the blue trend, which is our second cart, and we can pull off the maximum value of 0.277 meters per second. And then the minimum is going to be pretty close to 0. So couple of different ways to get that data. I had a brief moment of thinking about something else that might be useful to add into that conversation, but it's evaded me, so we'll just keep moving ahead. So that's the second of the three collisions. We've had the completely inelastic, and now we're gonna switch gears once again and get the Go Direct Carts up here. This time, since I'm disconnecting the LabQuest Mini altogether, I'm gonna restart graphical analysis altogether. I just won't save that. So here I am disconnecting my LabQuest Mini, so I don't have to worry about that anymore. Taking these carts off, and then I'll relaunch graphical analysis and connect my Go Direct sensors. So with the Go Direct sensors, power button on the side, make sure that the LED is flashing red, meaning it's ready to be connected. I'll get my other sensor cart up here and do the same thing so that we are ready to connect both of those. You'll get that red LED flashing saying, I'm ready to go. And then let me bring graphical analysis back over here. And this time, again, it's sensor data collection, but instead of having a LabQuest Mini and wired sensors connected, we're connecting to the carts. I'll point out here that, at the Vernier World headquarters, if you will, and there are a lot of Go Direct sensors around, I can do the proximity connect, which is great if I put the cart, right next to my computer, for example. Or I can simply use the filter here to say, this is my cart, and that narrows it down to these two. I know that we have the Y and a G. The Y is my yellow cart, so I'll click on that first. There we go. And then the green one is still waiting to be connected, so I'll go ahead and connect that as well. And then we see sensor channels here. I'll just click on this for your information. The sensor carts have position, force, and a 3-axis accelerometer built into them. We're only interested in position so we can get velocity data. So we'll just leave it as is, and I'll click done. And once again, let me go ahead and change my app preferences so we can see this a little bit more clearly. Okay. Now, with this sensor cart, I'm just leaving the receivers on there kind of as an end stop. You don't need to do that, certainly, but let me get the picture back up here in front for a moment. You see the arrow on the cart indicates the direction of positive motion. So if this cart here is on the track, moving this way, that's going to be in the positive direction. There's nothing that says I have to have the carts facing each other with this arrow facing backwards. I can just simply turn this cart around and just make sure that I have my magnet tabs facing each other so that when I'm pushing them together, the magnets are repelling each other. And this provides a good elastic collision where there's not a lot of energy lost at all. The carts actually never touch each other. They just come very close. The only trick to this is that they repel each other so effectively that you have to zero the carts one at a time. So I'll go ahead and get the blue cart. Well, it looks blue. We call it green. It's actually teal, kind of halfway in between. That's what the G stands for. So I'm going to go ahead and zero that. I don't get confused about which is number 1 and which is number 2 because they're labeled by their colors. So that's kind of handy. And have that with this point right at 0. Now I'll bring the other cart up and 0 it in place. And the Y is for yellow. We call it chartreuse around here, but that's what the Y stands for, not for the Y axis. So when you see, like here, if we look to velocity Y, that refers to the velocity of the Y cart, the yellow cart, not the Y axis or something like that. So a little point of clarification. So I'm going to bring this cart back to 0 and bring this cart back here to some point where I'm going to start it. And again, we're looking at a close to perfectly elastic collision with this. So we'll see what happens when we collect some data. And the end stop of the receiver worked pretty well. Again, I can click on the zoom to all data just to give us a little bit better view here. You'll notice that there is a little bit of a slope here. So in this case, the friction of the carts was not perfectly countered by the slope of the track. So in this case, I'm going to be looking for that point where it's pretty clear that that the collision has started, and probably looking at the velocity of the second cart, of the green cart, is the best indicator of that. So somewhere right in here. So we're looking at 0.34 roughly meters per second as my initial velocity for cart number 1. And then after the collision, so I'm just toggling along here until I get to the point where I seem to be at the peak velocity for cart number 2. So I'm going to have a velocity of 0.32 meters per second versus 0.33 or 34. Yeah, so there you have the data. Again, you would fill out the table with your data for velocities, and then go through the effort of calculating momentums and velocities for each of those carts, and then totaling those up. Now, I was thinking about how these instructions were laid out and was wondering, well, is there a way that we could do this with calculated columns instead of the actual hand calculations, if you will? And so I went ahead and did this, and I'm just going to want to show you the end result of my my experience with that. So let me see if I can find that file. I will not save that, as beautiful as it is. And there's the file that I created. So I'll go ahead and open that up. Oh, this will probably help if I disconnect these two carts at this point so they don't think they're still part of the picture here. And what I did in my data table is I calculated a momentum and a kinetic energy for each cart. So, and I used the particular mass. So let me just show you what this looks like. I added a calculated column. That's how I got there. I'm just going to show you what that calculated column is actually doing. So it's taking, for momentum, the mass of the cart, multiplying it by the velocity, and it's raising it to the power of 1. This just happens to be one of the pre-selected formats for calculated columns. It's, if you will, a times x to the b power. So my parameter is velocity. I multiply it by the mass. and it creates a column based on all the velocity 1 data, actually on all of my data sets. All of the velocity 1 gets converted into a momentum column. And we have that, I can grab that little tab and drag it away. I show that right here. So here we have for my last data set, momentum 1 and momentum 2 graphed. And I can look at this visually, which I think is actually very helpful to recognize that my momentum initially, my momentum finally are the same, generally the same within a reasonable order of error considering friction, etc. And then I've done the same thing for kinetic energy, just have a slightly different calculation. Because my masses are different, slightly different, I can accommodate that in my calculated columns. And again, I can take a look at, here's my energy before the collision, and here's my energy after the collision, and compare those values. I could create a total value as well if I wanted to look at if that total energy changes significantly. So I see in the chat somebody's asking about the labeling of the calculated columns. So let me just jump into that. So when I created the calculated column, I'll go to this one this time. It gives me, so let me just, I'll just show you this. If I add a calculated column, it allows me to put a name in here, whatever I want to call it, and add units in here, whatever I want those units to be. The units are not used for any type of calculations. They're just going to be whatever units you put in there. Excuse me. Grab a little glass of water there. The expression that's used, you click on this insert expression, and you get this list. Again, X's and Y's and Z's, if there's a Z there, here's a Z, are all data that you've collected. So they'd be columns of data that you've collected. A's and B's and C's are going to be parameters that you enter in a value for. So when I click on AX to the B, I enter the value for parameter A and the value for parameter B, and I select what I want here. I'll just cancel that now. So it looks like we're nearing our expected departure time. And I've actually kind of run through what I was expecting to cover. Josh, are there questions in the chat that would be worthwhile talking a little bit about before we depart these fine folks?
There was one question was about if you were going to do this lab with, say, AP students. You know, typically, especially in like AP physics, often you have, these are second-year physics students, so they know the law of conservation of momentum, and they have a pretty good idea of what to expect. The flip side is maybe you want to have a more like inquiry-based lab. How might you change or add to this particular lab to make it accommodate, to help it accommodate those classes as well? Mm-hmm. I have the fortune of I've been thinking about this while you were talking, so I have some answers. But I'm going to let you answer first while I answer another question in chat here.
Well, the first thing that comes to my mind is to set students up with requiring them to use carts of different masses and go through the same set of experiments and just see if that is a factor or not in that. But I'm curious as to what you came up with as you've been brainstorming.
One of the features of our both our Go Direct sensor cart and the standard, carts and tracks is that the plunger that's in there is has a trigger on it, and it has a trigger kind of on the top of the cart where you can manually like push the little button and it triggers. But there's also actually a button on the face of the cart, like just below the plunger itself, that with a little screwdriver, you can pop it out. And with that little external trigger there, you can actually create super elastic collisions where the plunger doesn't trigger until the two carts collide with each other, which is kind of cool. And you end up with a collision where momentum's conserved, but you end up with more kinetic energy than you began with. And for an AP class, that would be kind of a neat sort of thing. The students know they know collision momentum can be conserved, and with that trigger, that external trigger and the plunger acting on it, they might not sure know what to expect as far as, well, these two carts are going to come together and then they're going to explode like that. What's the energy going to do? And if they do this, they think to themselves, well, we'll probably end up with more kinetic energy before. They could do some work backwards and use that energy to figure out, well, maybe what's the average force exerted by the plunger? So there's a way to kind of extend that as well.
Yeah, that's a great idea. I think that's probably an underused tool, the release of the plunger by the two carts coming together. So
yeah,
that's great.
Yeah, Sally in chat also mentioned, that plunger too you can use to do where both carts start at rest and you trigger it and then they move away from each other. And that's especially cool if they have unequal masses. You talk about like an explosion.
It's hard to do when you have the magnets attached, though. I'll just mention that right
that's
now.
True. Yeah, you'll definitely want to swap around those tabs there.
So, good. Anything else from the chat?
I think.
I see John McClain is into pyrotechnics. That's always fun to liven up your class a little bit. Very good. Well, if you have more questions in the coming days, feel free to reach out to us at physics@vernier.com, and Josh or I or one of the other physics specialists will be glad to help you out. And we hope that your post-holiday labs are successful if you go into momentum and collisions.
All right. Thanks, everyone. We'll talk to you soon.